This is Sev, and he's a third-year mathmo at Jesus. Today he'll be giving a talk on local global principles.
Thank you so much. Before I begin the content of the talk, just to go over what we'll be discussing. The talk will basically be divided into three parts. The first part will be talking about localization and some of its properties. So for anybody who's done the GRM course, you won't have come across localization, but it's like not a difficult concept in rings. So we're briefly going to go over it and what its properties are. And then go to the next verse for the second part. The second part of the talk will talk about the local global principles. And these are really nice theorems about localization. And nice, I mean, both in the sense that they're simple and they're really powerful and they're quite beautiful. And then in the third part, we want to discuss why global principles work. So like, why do we have these principles? And in order to do that, we need to geometrically interpret that, which is a surprise because we're doing algebra. And we need to come up with the geometric interpretation of a ring using what's called the spectrum of a ring. Now, every now and then, actually, I'll say, you may have noticed I accidentally missed a verse there, the one about the Dark Lord and his dark throne. And any mistakes I make, of course, throughout, it's April Fool's Day, so I'll, of course, all April Fool's jokes, but please do notify me so I can change them. And every now and then, I'm going to say something slightly more advanced than the prerequisites, which is basically familiarity with rings. I assume that you have basic familiarity with rings, but every now and then I'll say something that's not basic about rings. They're not so advanced, but you may not know exactly what I'm going to say, but you don't need to care. And I'm going to always prelude that by saying, if you care about this, then blah, blah, blah. So if you care about this, then blah, blah, blah. You don't need to worry if you don't understand what I'm talking about. Because I'm just saying it for anybody in the audience who does care about what I'm talking about. And lastly, if you don't understand what I'm talking about, but I didn't say that, please do interrupt and ask any questions or put in the chat. I'm happy for anybody else in the chat to answer it if it's a straightforward question and you know the answer to it. But I probably won't look at the chat until the end of the talk. So interrupt me. I'm happy for you to interrupt. And now, before we begin the first part about localization, there are two things that I want you to bear in mind throughout the first and second part. These are points that are really obvious in the third part, but aren't so obvious from the definitions in the first and second parts. But I want you to have this intuition in the back of your mind. And that's first, the point is that localizations of rings are like a dual to a quotient of a ring. And this should be useful to you because you're probably quite familiar with quotients of rings. You've covered that quite a lot and you're familiar with its properties. Now, what does it mean for it to be a dual? You'll probably only come across duals in stuff like points and lines in a plane or a graph or vector spaces. So what does it mean for actions on your ring to be dual? It means that when you have a property about localization, there's generally a dual property, a mirror sort of property about quotients and vice versa. And the reason that these are dual is because the second point is that they basically correspond to quotient. Localization corresponds to focusing on a particular part of your ring, and quotienting quotienting is like ignoring a different part of your ring. And when I say that, I mean it literally. So the second point I want you to have to bear in mind is that there is a geometric interpretation of everything we're doing to our rings. And these are the geometric ways you can think of localization and quotients. So now we're going to begin part one about localization. And localization is just, you have a ring and you want to add some inverses to your ring because not everything is invertible. Say that you have the integers, then 2 isn't invertible. But maybe you have a matrix where the determinant is 2 and you want to invert that matrix. So you want an inverse for 2. So what you can do is you can just formally add an inverse. And actually you can formally add lots of inverses. So the integers localized at 2 is the ring with the integers plus an inverse for 2, or all fractions with the denominator 2 to the n. But you can also localize at lots of places. So you could localize the integers at everything but 2, and then your fraction a over b with b odd, right? So let's formally define this using a monoid, because we're going to deal with a ring, and always going to be commutative and with a 1 in this talk. So we define a monoid to be S, a subset of the ring, with 1 in it, and it's multiplicatively closed. So if A and B are in it, and AB is in it. Why do we localize it monoids? Because if you're going to be multiplying denominators or adding fractions together, then you have to be able to multiply the denominators together, right? So if you're going to allow fractions A and B at the bottom, you have to allow AB. So we're always going to localize at a monoid. Some people won't say that. Some people will localize at a set and see what it produces, and you get all the product. But we're always going to localize at a monoid for convenience. So let's just give you some examples of a monoid. You can have a monoid that's generated, sorry, my hand's a bit shaky. Let me rewrite that. You can have a monoid that is generated by a single element, and that's just 1s, s squared, and eventually, if it's nilpotent, then there's 0 in there somewhere, but if it's not nilpotent, then it's just an infinite set, which we're localizing at, and that's all the denominators of the form s to the n. You can also have a monoid A without P, so the entire ring without the elements in a prime ideal, and that's basically the definition of a prime ideal, is that the complement of it is multiplicatively closed. And we often so that's another monoid. And for example, in an integral domain, A without 0 is multiplicatively closed because 0 is a prime ideal in an integral domain. That's basically the definition of an integral domain. And then when you localize this, you get the field of fractions. And then the last one is the set of regular elements. Well, I don't need to write set. Of regular elements. And what does it mean for an element to be regular? It means that there's no x such that ax equals 0 if A is in this set. It means that it's not a 0 divisor. And the product of any two regular elements is a regular element, and 1 is obviously a regular element, unless in the trivial ring where 1 equals 0, but we won't localize at regular elements in that case. So we define the localization at S. It's often written one of these 3 notations, you'll see them all, as basically just fractions x over s with, or x over t I've written because s is hard to distinguish from capital S, with x in A and t in S. So we're just allowing fractions with the denominator in S. And what is the equivalence relation on the set? Remember, when you construct the rationals out of the integers, you have to have an equivalence relation to say when fractions are equal. It's actually slightly more nuanced than just multiplying out. It says that if there's this third s such that multiplying this gives 0, then you have their equivalent. And the reason for that is, you may remember in GRM when you proved that this does form an equivalence relation in Q, or the field of fractions, there was a slight nuance point with the transitivity of the equivalence relation, which is that you use the fact that it was an integral domain at that point. And if you have this third factor, then you don't need to use the fact that it's integral domains. This basically deals with the fact that some of your elements aren't regular. So we're going to give some examples. Our first monoid was generated by 1 element. So you can localize at 1 element, and that's just the same as adding an inverse in to your 1 element, and that's the same as this this ring, if you don't are more familiar with that sort of thing. And you usually write it as A localized at T. And then you'll often see, not in this talk, maybe at the end you'll see it, but most of this talk won't deal with localizations of primes. But in algebraic geometry, you'll often deal with localization at prime ideals, and that actually means localizing at everything except for a prime ideal, and that's often written with this notation where the prime is in brackets. So for example, if A is an integral domain, then localizing at 0 gives you your field of fractions. So in this way, localizing generalizes the process of getting a field of fractions. And then if you localize at 0, or a monoid containing 0, you get the 0 ring. And this is the same as quotienting by an ideal that contains a 1. And this is our first example of duality between quotienting and localization. Next, if you localize at the product of 2 elements, st, that's the same as first localizing at s and then localizing at t. And the reason for that is, say that you had fractions of 6, well, 2/6 is in your ring and 3/6 is in your ring. So this acts as a half and this acts as a third. So you've basically got a third and a half, even if it's not exactly written like that in your thing. And in fact, this generalizes more generally to if S is a subset of another monoid, then localizing the bigger monoid is the same as first localizing the smaller monoid and then localizing the bigger monoid. Now, for anybody who's really into universal properties of maps, there are the following universal properties. I put the localization map on top and the quotient map on the bottom. And this basically says that any ring homomorphism from A to B, where it sends the monoid to the units of the codomain, factors through the localization map. So you can factor through this localized ring by first doing the localization map and then applying some unique map. And the same is true about quotienting. If it instead sends the ideal that you're quotienting by to 0 in the codomain. And notice the similarity between and the sort of duality between these two universal properties, which is sort of why we get duality in the two in the properties of them. So some more properties about localization. The kernel of the localization map is 0 if your element is regular, or if your monoid consists of regular elements. But if you had x dot s and you were localizing it equals 0 and you were localizing at s, then you can cancel that off and you get x equals 0, and x may not have been 0. So the kernel in general of a localization map is the annihilator of the element. Everything that the product of it is 0. This is sometimes written in this conductor form. But yeah, so in fact the annihilation of all your elements gives you the kernel, and the ideal generated by them gives you the kernel of your map for a general monoid. And for an example of this, we're going to consider z/6. And now if we localize this at 4, well, we have 3.4 equals 0, so 3 equals 0. We have 5.2 equals 4. So writing this, remember that localizing at a product of two elements is the same as localizing at the divisors. So you can cancel a 2 and you get 5 equals 2. So we end up with z/3, right? Because 3 is 0. And if you instead localize at, we'll say this at 4, or the monoid generated by 4 is actually just 1, 4, because 4 is idempotent. And then if you instead localize at 3, then this gives you 3.5 equals 3. It implies that 5 equals 0. No, 5 equals 1, sorry. And 2.3 equals 0 implies that 2 equals 0. So we then get, let's just rub these workings out so that we can say that this is z/2. And essentially what's going on here, we have a ring with idempotence. We have a ring with idempotence, so we can decompose it into subrings z/2, direct sum z/3, and then we're localizing at 1, 0, and 0, 1. So that's the same as just quotienting by the other one. In fact, you'll notice that we get, let me just rub this out. You get the same effect if you quotient by 1 minus 4, which is 3. You get sorry, the other way around. You get, yeah. So if you quotient by 1 minus 4, which is 3, then you get z/3. And if you quotient here by 1 minus 3 equals 4, then you get the same ring. So there is this duality in this case as well between quotienting and localizing when you have idempotence, and you can and just as a note here, because it will come in useful later, rings have idempotence if and only if they can decompose the direct sum of subrings. And rings without any idempotence are called connected because you can't decompose them into a direct sum of subrings. And I wonder why, as a sort of facetious look to the last part of the talk, where we'll see why you use the term connected. And now we're moving on to part 2 about local global principles. Now, what is a local global principle? Well, lots of facts in maths, when you localize, stay true. Obviously not all facts. So for example, z over 6 has an irregular element we just saw, while localized at 4 it doesn't, it's a field. Conversely, stuff true about the localized ring may not be true about the original ring. So for example, z localized at 2 has, in z localized at 2, 2 has an inverse, while in z it doesn't. So we need to, if we want to preserve properties, we need to speak about specific properties, and then certain properties are preserved. For example, being regular in your original ring, then you're still regular in the localized ring. But what about if you're regular in the localized ring? Are you necessarily regular in the original ring? And the answer is no. Things that are true in the localized ring, even if you pick them carefully, are not necessarily true in the original ring. But if they're true in enough localized rings, so say that you localized z at 2, and then you localized it at 3, and something was regular both in z localized in 2 and z localized in 3, then in fact it will be true in the original ring. So we need to pick our localizations carefully, and then things that are true in all localized rings are actually true in the original ring as well. So we have this converse. So picking our localizations carefully leads us to the following notion, which is the notion of a comaximal monoid. So elements are called comaximal when the ideal they generate is the entire ring. And if you have monoids T1 up to Tn, then they're comaximal for anything you pick from any of them. So if you pick any T1 from the first one and any T2 from the second one, etc., etc., then the ones that we pick are comaximal. So those elements generate the entire ring as an ideal. Some examples of comaximal monoids: if Si are comaximal, then Sin are comaximal, because you can take the identity AI Si equals 1 to some power, I think it's n minus, 1 minus n plus mi, if you want to show that Si to the mi are also comaximal, because then you can just group terms. Next example, if A equals A1 up A2 up to Am, then the monoids A to the n, 1 plus A1A and 1 plus up to 1 plus ANA are also comaximal, because we have that for any BI we pick for them, then BI equals 1 minus AI xi. So modulo the ideal generated by AI xi, it's 1. So 1 equals AX when you product them all together, because A is the product of those. But then 1 equals A to the M X to the M equals 0. So we actually localize by the entire ring. So it doesn't really matter, because we're generally going to be using these ones, but it's nice to know that there are other comaximal monoids, and this is true for all comaximal monoids. So now we get to our concrete local global principle, which is that if A is a ring and S1 up to Sn are comaximal monoids in A, then for a matrix B with entries in A and a vector C with entries in A, the system of linear equations Bx equals C has a solution with entries in A if and only if for each I it has a solution in the ring localized at Si. And in my opinion, this is an insane result, and you might see why soon. I mean, it may not seem immediately insane. But the proof is very simple, so let's quickly prove it. Firstly, say that we had, firstly, going from a system of linear equations with a solution X to a solution in the localized one is simple. You just localize, it's the same solution because you have denominators X over 1 in the localized one. Second, next, if you had yi over, if you have solutions xi in each of the localized rings, we can write this as yi over si for yi in a vector in just in A and si in si. So we have byi over si equals c by our above assumption. Now, by the definition of localization we had before, there's some ti such that ti byi equals ti sic. We just like multiplied out, but you have to take into account that it could be not a regular element. And now, if you write, since sum of ai si equals 1 for some ai, because they're comaximal, we get the solution x equals sum of ai ti yi. And what have we done in this proof? We've essentially very sneakily got rid of the denominator. So if you multiply this by b, it cancels all the denominators because they're comaximal. It's very, very clever that this is true even for non-regular elements because you get this ti. And just a note about comaximal monoids, this is a constructive trick. These are finitely many monoids that we can actually write down. And in general, you're going to see local global principles in your life written as localizing at all primes or localizing at all maximals. These are all equivalent. But we're going to be talking about localizing at comaximal monoids because we can actually write down the comaximal monoids. And there's a geometric reason why this sneaky constructive definition actually works, which we'll discuss at the end. But the point is that these are actually equivalent for things called finite character properties, localizing at comaximal monoids and localizing at all primes or all maximals, which hopefully we'll be able to see at the end if we have time. But if not, then contact me and I'll send you the resources about that. So there's a abstract version of this theorem about systems of linear equations and the fact that systems of linear equations is a local global principle, i.e. bx equals c has a solution in the ring A if and only if it has a solution in all the rings ASI for SI comaximal. And the abstract version says that the direct sum over all maximal ideals of the A modules A localized at 1 plus m, which is the same as localizing at the complement of m, is faithfully flat. And if you care about that, then you care about that. But I think the concrete one is actually nicer because you can see what it means, and also it's constructive, whilst this one is not obvious, it's constructive. So we have some immediately corollary local global principles. And that's anything that can be worded in terms of linear equations having or not having a solution. So for example, A equals 0 is a linear equation. A regular is the non-existence of a linear equation. An ideal A is the whole ring, if and only if there's a linear equation which it satisfies. And an ideal is a subset of another ideal, if and only if there's a linear equation. So these are all local global principles, i.e. they're true in the original ring, if and only if they're true in all the rings ASI for SI comaximal monoids. A matrix having, this is an ambiguous M because it could be module, having rank smaller than or equal to R or greater than or equal to R, we can word these in terms of whether the ideal generated by the minors of degree R are 0 or the whole ring. So this is also a local global principle. And then for anybody who cares, a ring is coherent is also a local global principle. It can be written using stuff with syzygies. So a ring is coherent, by the way, if every finitely generated ideal is also a finitely presented ideal. Coherence is like a constructive version of materianity often. So you're often more interested in coherent rings than materian rings if you're into constructive algebra. So now we're going to discuss a slick GRM proof that can be done using this local global machinery. And actually, in GRM, you only prove this for a unique factorization domain, and we're going to prove it for a not even a domain, right? It can be any arbitrary ring. And the theorem in this case is that if f and g are primitive polynomials, then the product fg is also a primitive polynomial. And recall, for anyone who hasn't done GRM for a while, that f is primitive means that the content of f, which is the ideal generated by the coefficients of f, is the entire ring. And this has some important consequences, actually. The corollary is the Gauss-Joyal lemma that Cf of Cg to the n is a subset of, no, sorry. Yeah, so for some n. And that has some also important consequences, which is when you want to talk about what the regular and invertible elements of a polynomial ring is. So this is an important theorem, and we're going to prove it in complete generality. So first, suppose that we're dealing with univariate polynomials. In fact, we're just going to do univariate polynomials. The multivariate case is just a simple induction on the number of variables. So we have C of f equals C of g equals 1, because they're both primitive. So now we're going to consider the quotient ring B over C of fg, B over the radical of C of fg. And the radical is the set of elements A such that A to the n is an element of C of fg for some n. And we use no generality in quotienting by this, because if 1 is element of CFG, is an element of the radical of CFG, then because 1 to the n equals 1, then 1 is also an element of CFG. So what we want to do is we want to show that this ring is the zero ring, that we've quotiented by the ideal 1, because then 1 is in our radical and then 1 is in our thing, so this is equal to 1. So how do we show that this is the zero ring? Well, a ring being 0 by our corollaries before, it suffices to show this localized at any comaximal element is the zero ring. So we can pick comaximal elements by the coefficients of f, because they generate the entire ring. So we assume that one of the coefficients of f is invertible, because we can assume that because it's fine to localize, right? So from there, it's an induction. But I'm just going to give you a sufficiently general example, and you can fill in any of the other details of the induction. So say that f of x equals a plus bx plus cx cubed. Oh, wait, no, sorry. Plus, I knew there was something special about x squared, plus x squared plus cx cubed, and we just wrote a 1 here. It could be a unit. We're just assuming that this is the one that's a unit, because we're allowed to assume that one of the coefficients, we don't know which coefficient, we're just doing x squared because it's sufficiently general you get the idea of the proof. And then g of x is written as g0 plus g1 x plus g2 x squared plus blah blah blah. Sorry, this is plus blah 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 too. Now in B, we have that the C of fg is 0. So we have ag0 equals 0, because the coefficients of fg are all 0 in B. Then we also get ag1 plus bg0 equals 0. And we get ag2 plus bg1 plus g0 equals 0. So multiply this by g0 and we get bg0 squared equals 0, because this term vanishes. Multiply this by g0 squared, well, that term vanishes. That term vanishes because b0 squared is 0. So you get g0 cubed equals 0. But because we randomly, at an earlier point in the proof, decided to do by the radical instead of the actual thing, completely randomly, there was no ulterior motive. In fact, g0 equals 0 because we're in a reduced ring. I.e., if g0 cubed is in radical of C of fg, then so is g0. So actually, the first coefficient of g is 0. So we can write it as x times h with h of smaller degree, and so we get g equals 0, right? You just knock off the coefficients one by one, using this process, and you say that G equals 0. But then C of G is also the 0 ideal, but we said that it was the 1 ideal. So 1 equals 0, and we're in the trivial ring. Hence, when we quotient by square root C of f of G, we're actually quotienting by the 1 ideal. So 1 is in our thing, and so 1 is also in C of f of G. I thought that was a neat proof. I don't know if you agree. And now, some of the less concrete-minded in the audience will have seen that really, really nice, powerful local global principle and all its consequences, and be like, I don't care about systems of linear equations. Give me some nice abstract stuff. So I want to briefly speak about localizations of modules, because there's a really nice local global principle, which is a bit more abstract. So some of the abstract-minded in the audience will care a bit more. And it also generalizes everything we've done before. So our theorem before is actually a consequence of it, and it's a much more powerful general theorem. So yeah, I wrote for those who aren't yet impressed. We can also localize a modules at S, and that has elements M over S, where M is an M and S and an S, just the same as before. And for those who care, this is the same as extension by scalars through the localization. For some properties of this, if n is a submodule of M, then the localized n localized to S is also a submodule of M localized to S. And we have this nice property that taking a quotient commutes with taking a localization. That's actually really important in general, but we're not going to use it at all except for this special case. This is a big fact. Then, if phi is a linear map, then we get a linear map phi S, which is localized at S, and it's quite an obvious map, but you have to think about what linear maps are first, which is that if it takes an element of S, first it just factors out the S, so it's 1 over S times phi of M, right? So you just take out the denominators and then you apply your previous map. And it satisfies these. By the way, all these isomorphisms are canonical, and that's what I mean. By that I mean, you think about the definitions for 2 to 5 minutes, depending on how familiar you are with the definitions, and then you realize, oh, that's an obvious map. But you have to be familiar with the definitions first. So the image of phi is localized at S is isomorphic to the image of phi S. So same is true for the kernel and the co-kernel. These are really nice properties because it means that localization preserves exactness of sequences. And exactness of sequences, I suppose, is not something that I considered in the prerequisite. But for anybody who doesn't know in the exactness of sequences, you don't really need to care. But we say that there's this MMP as an exact sequence. And it's an important thing in commutative algebra for the reason that it lets you understand the objects in this thing. So, for example, a certain type of exact sequence is called a resolution, and a resolution is very, very much like a triangulation in topology. So, those who don't know what exact sequences may know that you can take a surface and you can triangulate it, you can cover it with triangles, and then because you know a lot about triangles, you know a lot about your surface. You can calculate its Euler characteristic or whatever you like. The same is actually true for these resolutions. So that's an idea of how important these exact sequences are. So localization preserving exactness is a huge thing, and this is why lots of commutative algebraists really like localization. So we have some modular local global principles, and the first two are just corollaries from our concrete local global principles, which says that everything with linear systems of equations is a local global principle. And the first one is that M is finitely generated is a local global principle. And that's pretty nuts as well, because if you remember from GRM, if you have N as a submodule of M, N isn't necessarily finitely generated. Any quotient of M is, and any localization of M is. But this actually says the converse, that if your localizations are finitely generated, then so is your original map. And also, again, M coherent, that every finitely generated submodule is finitely presented. And we have a new local global principle, which is pretty nuts. which is that a sequence being exact is local global, right? So this implies that the local sequence MSI, where we've localized the maps as well, is exact. We saw that above. But if this is true for all the SIs, then it's also true for the original local global principle. And the proof of this, I'm not going to prove. It's a mixture of diagram chasing and what we did above. But this is insanely powerful, and it has some immediately corollaries which are easy to understand, which is that a linear map being injective or surjective is also true about its localizations, and is only true if it's true about all of its localizations. So now we're going to get to the part 3 of the talk, which is there are these really, really, really nice local global principles that we've just seen, and they're kind of nuts, and they're kind of insanely powerful. But I went on and on about at the beginning of the talk about how localization and quotients are just duals of each other. So why aren't there quotient global principles? Why can't we have nice theorems about quotients? Why does localization get everything? And the answer to this is to do with something slightly more advanced, and it's a geometric answer, which is quite surprising because we're dealing with algebraic objects. And this was the big revelation of Grothendieck in, I think it's the 1960s, I could be wrong, but it's sometime in the 20th century, that you can discuss all these properties geometrically, and actually there's a way to understand this geometrically. Now I have to warn you, everything we've done so far is constructive. What I'm about to do is not constructive. There is a constructive counterpart called the Zariski lattice, and it's a bounded distributive lattice, and entailment generates a locale, but I don't know anything about pointless topology, so I couldn't give you any geometric intuition about what this means. So we're going to deal with this nice simple, I say simple, ironic, well, semi-ironically, spectrum of a ring, because we can understand it even if it's non-constructive. Also, I probably won't cover the spectrum of a ring to the level that I want to cover it, because 20 minutes really just isn't enough time to give all the examples that you want to give. But without further ado, let's define it. And let's first talk about the motivation. So lots of rings come from functions on spaces. In analysis, for example, you consider the ring of continuous functions on a compact Hausdorff space. And we said compact, so it has a 1. And can we, oh, wait, maybe it will have a 1 anyway. I'm not an analyst. Can we recover the space from the ring of continuous functions? Is an interesting question to ask yourself if you're that way inclined. And the answer is yes. I mean, we consider the maximal ideals in our ring of continuous functions, and those are generated by continuous functions that vanish at a single point. Because if it vanishes at 2 points, then it's contained in one that vanishes at 1 point. And if you quotient by something that vanishes at 1 point, then you get stuff that vanishes at no points, and those are obviously units. So if you quotient by them, they're a field, so you have maximal ideals generated by this. So if you consider the space of all maximal ideals, then you recover the original set from your maximal ideals, because they each correspond to a point. And in fact, they also recover the topology, which is a surprising fact. This is called the maximal spectrum of the ring. But in general, we're not working in topology. We have far simpler rings, and we have to consider, as a result of this, more generally, all the prime ideals. So the spectrum of a ring is just the set of all prime ideals. That's the first off. Okay, we'll just take all the set of prime ideals. Maybe it's a bit weird that we're taking all the set of prime ideals, but we are. But actually, we can define a topology on this. And it turns out to be a very natural topology. So one way we can define it is through the closed sets. The closed sets is for every an ideal in the ring, there's a closed set corresponding to it, which is the set of prime ideals that contain that. But remember that the set of prime ideals in spec A are just points. So they're just points. We're considering a set collection of points. But in the ring, they're ideals. They contain your ring. And using some Zorn lemma thing, you can say that this is non-empty. Or we can define it using the basic opens, which is that for every element in our ring, we can define the set of basic opens to be the set of prime ideals that don't have that element in it. And that's the same. I'm going to leave it to you to show that that's a topology. There's one subtle point, which is saying that if a product of ideals is in P, then also one of the ideals is in P. So we log A as a subset of P. Otherwise, it's a simple proof, but verify for yourself that it's topology. We don't really have time. So some properties of the Zariski spectrum is P closed. A point in the spectrum is closed if and only if it's maximal. That's because it has to be not contained in any more prime ideals. And every prime is contained in a maximal ideal, supposedly. Generally, the space is not Hausdorff. So you're probably used to Hausdorff topologies, but this space is generally not Hausdorff. Then some more nice properties is that it's connected if and only if, so the spectrum of the ring is a connected topological space, if and only if the ring is connected in the sense of not being able to be decomposed into subrings or not having an idempotent. And you'll see later, idempotents actually correspond to clopen sets, so sets that are both closed and open. And Noetherian, if Noetherian, the topological space is Noetherian, which means that it has every set of closed sets has a minimal element, or every set can be decomposed into irreducible, if and only if the ring is Noetherian. So this is why you start to see random topology lingo and ring lingo being merged. Why is they're connected in commutative algebra? Because of this feature. And then 5 is a big thing, and it's that it's compact. And actually, I'm just going to briefly explain the proof of this. I'm not going to say all the details, but just the key points of it, which is that you have some sum of ideals which equals the entire ring, and you want to show that a finite subset of that is the entire ring. Well, if the sum of the ideals is 1, then 1 equals A1 plus A2 for some elements of the ring. But then we just picked out the ideals which generate 1. So actually this finite subset generates the ideals. So 2 important ideas mean that it's compact. Firstly, every infinite sum is actually just a finite sum. Like, you can't infinitely sum things in rings. Algebra just doesn't let you do that. Even in stuff like the ring of formal power series, ring of formal power series, you can write infinite sums of elements, but they're actually just finite sums of these weird elements, which are written as infinite sums. And the other huge thing is that it has a 1, right? Sometimes you'll consider rings, which are rings that are 1, and they're not compact, they're locally compact. And this is big in analysis. If you're into analysis, you might like the ring of functions with compact support, which is a locally compact. So the fact we have a 1 which sort of bases our space gives us compactness as well. And why is this so important that it's compact? Well, it means that we only ever have to talk about finitely many things at a time. Everything that we do when you talk about localization, all primes or all maximal ideals, well, that's just like a cover, and we don't need to cover with all the primes or all the maximal ideals. We only need finitely many covers, and this is why we get these co-maximal monoids, which are covers. In fact, you can think of these as partitions of unity of the spectrum. This will become clearer in a moment, by the way. I'm just saying this so that you understand why compactness is important for us, which is considering constructive commutative algebra. Basically, compactness allowed a sneaky definition of co-maximal monoids to work. So this is why lots and lots and lots of commutative algebra is constructive, because rings are really very finitary objects. And for suitable properties, this is the same. Sorry, I left myself some space there, which I probably should have used rather than all bunching it up. So some examples of the spectrum of a ring, so that you have a an intuition. The zero ring is just the empty set. Why? Because there are no prime ideals in the zero ring. It's not an integral domain, so the zero ideal is not a prime ideal. A field gives a point, a generic 0 point. That's because there's only one prime ideal, which is zero ideal. So these have the obvious topology, the empty topology, and the point topology. Okay, let's deal with a more complicated example then. Say that we have the integers, right? So we know the prime ideals of this. This is 0 and p for every prime. So p is also maximal, so they're closed points. 0 is not maximal, but so it's this this non-closed point, and its closure, you can see, because it's contained in every prime ideal, is the entire ring. So we have this, like, let's just draw Z, and we have these points, 2, the ideal 2, the ideal 3, the ideal 5, and these are closed points. I hope that I've got the primes right. And we also have this, like, generic closed point which takes up the entire line, which is the 0 point. Okay, that's weird. We have a point which whose closure is the entire space, but we expect it because we're not in a Hausdorff space. What happens if we localize it? What happens if we add in a half? Well, suddenly 2 is not a prime ideal anymore. Everything else stays the same. But if we localize a half, we cross off that element. So we get the entire thing except for 2. What if we localize at everything except for a half? Well, then we just cross out everything else. Right? So localization corresponds to taking a subset. So if you wanted to focus on the ideal 2, you would localize it everywhere else. And if you wanted to focus on everything else, you would localize it too. It's a restriction to the subset of the spectrum. And in a sense, it's a restriction to the points where they're not, where what you're localizing to is non-zero. So we sort of think of 2 as a function that vanishes at 2, which is weird for now, but you'll understand why in a moment. But 2 doesn't vanish on this. It takes non-zero values. Similarly, 3, when you the ones that localize everywhere else don't vanish here. And actually, numbers acting as functions on prime numbers like this way, where they have zeros and poles, is the core of Grothendieck's philosophy. By the way, just as a brief example for anyone who cares about why it's called a spectrum, when you add a linear map, sort of, like Kx, where x satisfies the characteristic polynomial of the linear map, or the minimal polynomial of the linear map, then the spectrum is the set of eigenvalues. So that relates to, in quantum mechanics, the spectrum of light, the eigenvalues. I gave myself too much space again, so let's scroll down a bit more. Right. We want to see what the effect of localization is on the spectrum. So what is the spectrum of AS, where you've localized it somewhat? So we have 2 maps. Well, we have one map, we have the localization map, but this sort of induces 2 maps on the ideals. Well, firstly, we can send an ideal to the image of the ideal. So we go A to J of A, but is this an ideal? Not necessarily, right? Because we may not have got enough denominators. So we can then consider the ideal generated by that. So this is called extension. Alternatively, if you have an ideal in this ring, then taking the pre-image under the localization map is an ideal. So you can go backwards, and this is called contraction. And it turns out that if you go back once and then forward again, so if you contract then you extend, it's the same as what you get. So B is the ideal generated by going backwards and forwards, basically. And the proof of this is simple. Firstly, obviously, J of J inverse of B is a subset of B. Now suppose X is B, in B. I'm going to show the converse. X is the form R over S for S and S. Multiplying by S, because S is in the ring, you can get that R over 1 is in B. So R is in the pre-image. Then when you send it back, R over 1 is in that one. But then when you take the ideal generator of that, you can multiply by 1 over S, so you get X back again. And the point is, this has a left inverse, right? So this map going that way has a left inverse, so it's injective. No, sorry, going, yeah. So it's injective, and ideals of the localized ring AS is a subset of the ideals of A, and I realize I need to slightly hurry. In particular, we have a map. So the localization map calls an inclusion from the spec of AS into the spec of A. So here I've drawn the spec of A, and these are the points where S sort of vanish. If you view them, if we just pretend for now that S, elements in S are functions on spec R, and they have zeros at these prime ideals that they're contained in. So obviously, if S is in P, then localizing S means that 1 is in P. Sorry, S is an element of P, then 1 is in P. Then P is no longer a prime ideal, because we want prime ideals to be proper. So that removes the point. So we remove these black lines, and we're left with all the ones where they're not contained in. The primes disjoint from S, because all the other ones become 1. So this blue is the spec of AS. So we're going to give a big example now, just so you can get a real handle on it. So say that you have CXY, the ring of polynomials in 2 variables. Firstly, what does the spectrum of this look like? What is the spec of CXY? Notice that we're using the complex numbers, so we've really gone off the constructive bandwagon. Well, we have the zero ideal, which is this generic non-closed point whose closure is the entire spectrum. And then we have a maximal ideal x minus alpha y minus beta, which are of the form, so which we can identify with points in the complex plane. So we have these points which are alpha beta for each prime maximal ideal. And then we have prime ideals, irreducible polynomials such as y squared minus x cubed, which correspond to sort of like curves of the points in the complex plane we satisfy. So we have this weird topology of curves in the complex plane that are satisfied by algebraic equations. And now, what happens when you localize these or quotient by these? Well, let's consider, I may have missed out a case. If I did, then let me know. Consider the cases. Well, if you localize by 0, you get the 0 ring. So you get the empty set. If you quotient by 0, you get the same thing. Blah, blah, blah. If you localize by a maximal ideal, then you've essentially taken that point and you've crossed out all the other points. And you also have the faint wisps. You still have the 0 ideal, so change color. And this, there's this generic point in the background, and otherwise you have faint wisps of lines that went through that point because they sort of stay in the localized, or like half of them do. And then for while quotienting by it, you get a field, so you just get the point, right? And then say that we have a irreducible polynomial, some other p not maximal. If you were to localize by it, I realize I'm going a bit over time. I'm almost almost finished. Sorry. If you localize by it, then you take essentially you get rid of all the points on it, but you have this line still, and you have the generic point around it, and the wisps of intersection. If you instead quotient by it, then you just retain the line and all the points on it. So this is localization at P. Sorry, well, A is the ring of complex polynomials, and this is quotienting by P. Quotienting gives you all points inside something, while localizing takes all things outside and nearby. And I've written up the correspondence slightly more below, which is the spectrum of the ring localized at P consists of points whose closure contains P, while the spectrum of the ring quotiented by P are points in the closure of P. In the spectrum of localized, P becomes maximal, while in the quotient, P becomes minimal, it becomes the zero ideal. Here you can see it becomes a local ring, so P becomes maximal. And in here, P becomes the unique closed point because it's maximal, while here P becomes the zero, so it becomes a generic non-closed point, which is as far as you can get from being a unique closed point, right? If your closure is the entire thing. So now the last part about the spectrum, we want to define functions on spec A. So technically, as well as a topology spec A can be given another structure called a sheaf, which is, I'm not going to go into the details of, but it's basically you define a bunch of functions on it. And the idea is that the same in the original one where we're trying to recover the ring from the space from the ring from the space, right? So you have the continuous functions on the compact Hausdorff space. So what do we do? Well, we can consider an element of A as a function on the space. Why? Because at each prime ideal, we can look at its image under the quotient map. So what is F in mod P, right, in A over P? So we can sort of think of spec A as this set of points, or maybe lines and stuff. And then there's these fibers above each point, which are the localized, are the quotient ring of the prime ideal at that point. And we view F as taking it to each one, right? So each F mod P for each point, right? But that's a really weird function, right? That does not like behave like normal functions. Its codomain is perfectly normal. It's the spec of A, but its domain is perfectly normal, but its codomain seems to be varying as you go through spec of A. What is it going to, right? So I'm not going to say exactly what it's going to, but this is what it's doing. This is what it's doing. It's taking each point and it's taking it mod P. And just as an example, you could consider C of X, and the same as before, it's sort of like a line where you have maximal ideals X minus alpha. If C is algebraically closed, we don't have any irreducibles, so we actually just have sort of like the complex plane. And then you can consider F in C of X, given by F of X equals X squared. Sorry, I'm just gonna, actually that is fine, because what I'm gonna do is I'm gonna redraw this slightly lower. So you have the set of points in the complex plane, maybe there's 0, 1. By the way, I'm like set of points in the complex plane, we're viewing it as one-dimensional, weirdly, but I'm not going to draw it. So what do we do? Well, at 0, we draw the A over C over each thing, X, and C of X over X minus alpha is just C. Right, there's just a field with a copy of C, not for the 0 ideal, there it's still C of X, but we'll ignore the 0 ideal. And what does it take well, at X equals 0, minus 0, it takes the value 0. X minus 1, it takes the value 1. X equals 2, it values the value 2. So we've essentially just drawn the graph of X squared when you quotient in this way. Another example could be Z, and then you have the prime ideals as before. And say that you had the function 3, then this is 1 here, 0 here, 2 here, etc., etc. Wait, no, 3 here, and 3 for the rest of it. And you want to ask, is this ring of functions, is the ring of functions defined this way on spec A your original ring? And the answer is no. So for example, what is the 0 function? What if you're 0 on all these things? You are, so say A is the 0 function, then A equals 0 mod P for all P in your ring. Well, I can give you an example of something that satisfies that. Well, if something is nilpotent, then A n to the n equals 0. So A to the n is an element of P for all P because 0 is in P, but then A is an element of P because the complement is closed under multiplication. So you have non-zero elements, which are 0 functions. So you're not getting your original ring back. In the case of Z, you do, but in most cases, you don't. So this is wrong. We picked the wrong notion of functions. And in fact, it turns out that the intersection of all primes, by the way, is the nil radical of 0. But we want to instead consider the weirder one, which is instead of localizing, of taking the quotient, we take the localization at each point, and we view the image under the localization map. And if we do that, I think I've drawn it below. Yeah. Oh, I've already done that bit as well. See, past me is much cleverer than future me, present me. So yeah, we try attempt 2, and now if f is 0, then f is equal to 0 for s and p for all p. But then that is 0, because if you localize at all primes, you have to take my word on it. That's the same as localizing at comaximal elements, and then you can just sum them to get 1. Or if you want a direct non-constructive proof, look at the annihilator of f. So for example, let's consider f equals 18. Then it's 18 over 1 here, but it's actually 9 times a unit here, so it's different, and here it's 2 times a unit, while everywhere else it's just 18 as it was before. So we still can consider them vanishing at that point. And what if we consider a more complicated example? So say that we had something like 55 over 18. Then it's not even defined at these points when you localize this, but it is defined all these places at these local rings, because here you don't have an inverse for 2 or 3, right? And it vanishes at 5 and it vanishes at 11 if I'd have drawn it on. And yeah, so now we can view rational functions as also on our spectrum. So there are lots of functions that are defined at some places and not at other places, and in posh language, you have a sheaf on your rings. But when you consider functions that are defined everywhere, that is your original ring. In posh language, again, you have the ring of global sections on the structure sheaf of spec R is R. You don't need to think about it like that. You just need to think that the globally defined functions is your original ring. And that's a marvelous, amazing fact, because now you're able to think of your ring as functions on your spec of R that are defined everywhere. Generally, this way of defining the functions is distinct from the other way of defining the functions. So the globally defined functions on the other one, what's called the global sections, is not R, except for sometimes, and sometimes they're the same. And one example is Z, and they're called the dual the other one's called the dual spectrum, and this one's called the spectrum. And that's why if you Google local global principles, the example that comes up is in number theory, and it's called the Hasse principle, and it uses quotients. It uses mod p, not localizations. You basically patch together linear equations mod p. So conclusions: why do local global principles work but quotients don't? Well, three things are contributing to that. Firstly, I mean, I didn't really say what a sheaf property is, but it basically says if you have two sets where here functions are defined, here functions are defined, and there's one function that agrees on the middle, then actually there's a bigger function that agrees on the whole thing. So you can sort of like glue together locally defined functions. So the first thing is that O spec A is actually a sheaf. So you can glue together locally defined functions. So localizations, you can glue them together. That's what we want to know. Then next, why does our localization work? Well, D of Si, what I defined at the beginning is the set of prime ideals that don't contain Si, is a cover, because AI Si is the sum of AI Si is 1. So when we glue them together, we get the whole space. So we get a globally defined function. So our localizations glue together to get something about the globally defined functions rather than something about the locally defined function. The point is we can do this part because it's compact. And then finally, and probably maybe the most important bit, is that the ring of globally defined functions is actually R. The globally defined function is actually A, rather than some other ring, like it is with the dual spectrum. This means that when we talk about the globally defined functions that we got from the gluing, that we got from the cover, it's something about the actual ring rather than some other ring. So we relate it back to the original ring. Just some further conclusions for anyone who cares is that, yeah, so taking global sections of a sheaf sort of preserves logic, it preserves colimits and other important stuff. So when you have your local ring and you pull back to A, the nice properties stay true. And following on with this, if you're true in sort of like your spec A, you can sort of pull that back to the where X I've written here is the space of all localizations glued together. And when something, if there exists something in spec A that's true, this provides a sort of open set in your X. And because there's a global cover, you talk about your whole X. So when you go down back onto your ring, yeah, it's true. And the point is that when you pull that back, properties stay true. You don't break up the properties because taking global sections preserves logic. Okay. Technically, my talk is finished. I'm happy to stop there. If anyone wants, I've written a sort of like dictionary of terms where you can convert between geometric and algebraic notions of rings. So here, a ring corresponds to the spectrum. The prime ideal corresponds to a point in the spectrum. Maximal ideals correspond to closed points, and elements correspond to functions on the spectrum. Then any arbitrary ideal, you get a closed set. Local rings correspond to local rings of functions defined near P in the sense above. And localization of F corresponds to the sort of like complement of the prime ideals where F vanishes. And localization of S are intersections of these. And idempotents correspond to closed sets, and modules, we haven't covered modules, but I'm told, I don't know myself, they apparently correspond to sheaves on your spec. So yeah, I mean, that's all I really had to say. Does anyone have any questions? So if there are no questions, I'm over time, so I won't go on. But I'll just note that I wanted to say at the end a few things. Just like, firstly, it's worth just looking at basically the three properties, or I'll just write them down. The three properties of what makes something a actually, will I? Yeah, never mind about that. Sorry. The two extra things that are constructively relevant is this stuff called finite character properties. So you probably won't find this except for in the book that I used for this, or I learned this from, which is, I'll reference you to Lombardi and Kit. Commutative algebra. It has quite a long name, so this probably wasn't wise. Constructive methods, finite projective modules. So if you're interested, in more, it's in that book. I mean, you probably shouldn't learn about the spectrum for that book, or like the Zariski lattice for that book, because there are better ways to learn it than constructively. But I mean, for the finite character properties, which is true, the properties that are, if they're true constructively, then they're true classically. But that's like a classical proof rather than a constructive proof, because otherwise they would be constructively equivalent, which they're not. That's in that book, or contact me and I can send you some references. The other thing I wanted to talk about is, just briefly at the end, is also in that book, is there's Zariski lattice. So just to briefly define, actually, in case we had time, I wrote some stuff below. Scroll down. Yeah, so the Zariski lattice is defined as the set of radicals of finitely generated ideals, and 0 is defined as the radical of 0, and 1 is defined as the radical of 1, and meet is defined. Oh, is it meet? It might be join. I think it's meet. And meet is defined as the one with the sum, and join is defined with the product, or possibly the other way around. Yeah, I'm not going to go into that, but some nice properties about the Zariski lattice is it's a Boolean algebra if and only if the ring is 0-dimensional. Connectedness is still connectedness of the lattice, and projection onto finitely generated ideals, and gives you a quotient lattice setting the ideal to 0, and localization at a finitely generated ideal also gives you a quotient lattice setting it equal 1. So you have the same duality, which I've written between the ideals and the things you localize at. And entailment generates something in pointless topology, and I don't know anything about pointless topology, so I couldn't tell you about that. But apparently it's basically just as strong as the spectrum, I'm told. So yeah, if nobody has any questions, I suppose.
Yeah, I guess there are no questions. So on that note, thank you very much, sir, for the talk and also for the recommendations of the books. Yeah, thank you very much, everyone, for coming. This was the first event of the term, and keep coming back every week.
Yeah, thanks for everyone for coming.